Chapter 3, Section 4, Applications in Data Science, Vector Space Models. We can apply vector spaces in various fields of machine learning. One of the notable examples is Vector Space Model, VSM. It is an effective way to represent and analyze data, particularly when dealing with high-dimensional datasets. In this section, we will explore what vector space model is, how we can use it in machine learning, and why it is so effective. A vector space model is a mathematical model that represents objects as vectors in a vector space. These objects include documents, images, or any data points. The fundamental idea of vector space model is to transform qualitative or high-dimensional data into a structured numeric form that can be easily manipulated and analyzed using linear algebra techniques. In vector space model, each object is represented as a vector, and each dimension of the vector corresponds to a specific feature of the object. The values in a vector represent the magnitude or presence of these features. For example, in a text analysis, a document can be represented as a vector where each dimension corresponds to a unique word, and the value in each dimension represents the frequency of that word in the document. Vector space models are used extensively in data science. Let me show you some key applications. The first is text analysis using natural language processing, such as document classification, sentiment analysis, and topic modeling. By representing text data as vectors, we can apply mathematical operations to compare documents, find similarities, and categorize them. Let's focus on document similarity as an example. Using vector space models, we can measure the similarity between documents by calculating the cosine similarity between their corresponding vectors. The cosine similarity measures the cosine of the angle between two vectors, providing a measure of how similar the vectors are, regardless of their magnitude. If v1 and v2 are the vectors for two documents, we can quantify the similarity between the two documents using this formula. If the cosine similarity is 1, the two vectors are in the same direction, and thus the documents are identical. If the cosine similarity is 0, the two vectors are orthogonal, and thus the documents are completely dissimilar. If the cosine similarity is somewhere in the between, the documents are partially similar. Let's consider a simple dataset of 3 documents. Data science is fun. Machine learning is fun. Data science and machine learning are exciting. To build a vector space model, we first create a vocabulary of unique words from all the documents. Now, we represent each document as a vector in this vocabulary space, where each dimension corresponds to one of the words in the vocabulary. We can use the term frequency, that is, the count of each word in the document, as the value for each dimension. We can convert this term frequency table into vectors. Here, each vector represents a document, and the vector's dimensions correspond to the words in the vocabulary. Another typical application area is image recognition. In image recognition, vector space models are used to represent images as vectors, where each dimension could correspond to pixel values, color histograms, or other image features. These vectors can then be used in various algorithms for image classification, object detection, and image retrieval. As with the case of text analysis, we can quantify similarity between images using cosine similarity. As an example, imagine you have 2 small grayscale images, each represented as a 2 by 2 pixel grid. Each pixel has a value ranging from 0 to 255. For a grayscale image, a pixel value of 0 represents black, and that of 255 represents white. Step 1. Convert images to vectors. We can represent each image as a vector in a 4-dimensional space, where each dimension corresponds to a pixel value. To measure how similar these images are, we calculate the cosine similarity between the two vectors. The dot product of v1 and v2 can be computed in this way. Then, let's compute the magnitude of v1 and v2. Now, let's compute the cosine similarity. In this case, the cosine similarity is very close to 1, meaning that these two images are nearly identical. As another example, let me show you a case of color image. Imagine you have two small color images, each represented as a 2 by 2 pixel grid. As to color image, each color pixel is represented as a vector in 3D space, red, green, and blue values. So, 4 pixels by 3 channels, resulting in 12 elements. So, we can flatten the 2 by 2 pixel grids into vectors of 12 elements. As with the case of grayscale image, we can quantify the similarity between these color images using cosine similarity. You might think that understanding a vector is sufficient to calculate similarity, such as cosine similarity. It is true. However, the concept of a vector space adds deeper meaning and generalization to these operations. Let me clarify the difference between a vector and a vector space. A vector is simply a sequence of numbers. It represents an object through its features. For example, in text analysis, each dimension corresponds to word frequency, while in images, each dimension corresponds to pixel values. On the other hand, a vector space is like a field where vectors exist. It gives more meaning beyond just a sequence of numbers. In a vector space, there are rules for operations like vector addition, scalar multiplication, and calculating angles and distances between vectors. So, why vector spaces matter? There are several reasons. First, ensuring the validity of vector operations. Second, understanding dimensions and features. Third, meaning of distance and orthogonality. Fourth, transformations and dimensionality reduction. Let's explore these reasons one by one. Vector spaces matter, ensuring the validity of vector operations. The concept of a vector space enables us to add vectors or scale them by a scalar. Without this concept, we would just be manipulating numbers without understanding why these operations are valid. For example, adding vectors of documents to create new document vectors is a valid operation owing to the vector space structure. Without the vector spaces, it would be hard to justify why these operations make sense. Second, understanding dimensions and features. In a vector space, the dimensions are important. Each dimension represents a feature, such as words in a document or colors in an image. By understanding how these dimensions are designed, we can not only compare vectors, but also understand which features create the differences. For instance, in an image vector space, dimensions might represent pixel values, which helps capture the differences between images. Third, Meaning of distance and orthogonality. In a vector space, distance and angles are also considered. Without the concept of a vector space, we would not be able to measure how far apart two vectors are, or how similar they are. Specifically, when two vectors are orthogonal, that is, the cosine similarity equals 0, it means that the two data points are completely unrelated. For example, if two documented vectors are orthogonal, it indicates that their content is entirely different. Fourth, transformations and dimensionality reduction. With the concept of a vector space, it becomes possible to transform data into different representations or reduce dimensions. Techniques like principal component analysis or TSNE rely on vector spaces to reduce dimensionality while retaining as much information as possible, enabling us to identify similar data points efficiently. These dimensionality reduction techniques will be covered in subsequent chapters. Let's summarize the key points. The concept of a vector space goes beyond just manipulating vectors. It provides a structure and rules that enables us to understand why operations like addition, scalar multiplication, and similarity measures are valid. While we can calculate similarity with just vectors, understanding the structure of vector spaces enables us to grasp deeper relationships between data and perform other operations like dimensionality reduction and feature extraction appropriately. Knowledge of vector spaces provides a foundation for understanding how data is combined, compared, and transformed, making it an essential concept for dealing with complex data relationships. Thank you for watching. Please thumbs up and subscribe to my channel.